China is shipping silicon carbide power chips into electric vehicles, grid inverters, and industrial systems right now, in real volume, at competitive prices, with customers outside China buying them. On paper, that looks like a sovereign supply chain. But there is one object inside every one of those chips that tells a different story: the wafer it was built on. Trace that wafer back to its source, and, in most cases, the line goes abroad. Industry estimates suggest that China's domestic self-sufficiency in silicon carbide substrates sits at only around 20 to 30%. Reported figures, not independently verified, but consistent across multiple industry analyses. That means the floor beneath China's most advanced power chips is still mostly imported. The companies supplying that floor are primarily American: Wolfspeed, originally founded as Cree, and Coherent, formerly known as II-VI. They grow the crystals. China processes them. This is not a story about China failing at semiconductors. The chip fabrication end is genuinely strong, technically real, commercially competitive, and exporting. The question is, what sits underneath it? Because the wafer is not a commodity input the way copper wire or packaging resin is. Its internal structure, the density of its atomic defects, determines whether the chips built on it function at all. A compromised substrate does not produce a mediocre chip. It produces a dead one. So what exactly makes this particular crystal so hard to grow? And why can't a country that has mastered chip fabrication simply replicate the layer below it? Those are the questions that actually matter here. And the answers have less to do with politics or policy than with the physics of matter at extreme temperatures. Silicon carbide is a wide bandgap semiconductor. That phrase matters because of what it means in practice. Silicon carbide power devices can switch electricity at higher voltages, higher temperatures, and higher frequencies than standard silicon can manage. That is why they are the preferred switching component in electric vehicle inverters, in fast chargers, and in the grid infrastructure connecting renewable energy to the transmission network. The material's electrical properties make it essential to the hardware stack of the energy transition. Those same properties that make silicon carbide so useful also make it extraordinarily difficult to form into a usable crystal. Silicon, the material that built the entire semiconductor industry, melts at around 1,414 degrees Celsius. You can grow it into a perfect crystal cylinder by dipping a seed into the melt and pulling it slowly upward, a process that is difficult but well understood and fast enough to be commercially practical. Silicon carbide does not melt under normal conditions. Instead, above roughly 2,700 degrees Celsius, it sublimates. It converts directly from solid to gas, skipping the liquid phase entirely. That temperature is hotter than the surface of the sun. Because there is no melt to work with, the standard crystal growth method that built the silicon industry simply does not apply. Instead, silicon carbide manufacturers use a process called physical vapor transport. The silicon carbide source material is heated until it vaporizes, and that vapor is then condensed onto a seed crystal, molecule by molecule, inside a sealed furnace operating at extreme temperature. The crystal grows slowly, on the order of millimeters per day, qualitatively speaking. The resulting cylinder of solid crystal is called a boule. Slice the boule into discs, polish those discs to atomic flatness, and you have a substrate wafer. Imagine trying to grow a perfectly ordered ice crystal, not by freezing water, but by condensing steam inside a furnace hotter than any flame, while keeping every molecule landing in exactly the right position. One stray contaminant, one pressure fluctuation, 1 degree of temperature variation in the wrong direction. Any of these can collapse the crystal's internal order into defects you cannot see with the naked eye. Defects that will only reveal themselves when you slice the boule, test the wafer, and find out what you lost. The critical question people ask at this point is, can't you just buy better furnaces? The answer is that the furnace is necessary, but not sufficient. The process knowledge, the exact temperature gradient across the growth chamber, the seed crystal preparation protocol, the gas chemistry, the contamination controls at each stage, is what determines whether you produce a low-defect boule or an expensive piece of compromised crystal. That knowledge does not live in the equipment. It lives in the engineers who have run thousands of production cycles and learned from each one what the next one should look like, which is precisely why the companies that got there first carry an advantage that capital expenditure alone cannot rapidly close. Wolfspeed has been growing silicon-carbide crystals since the late 1980s. That is more than 3 decades of production cycle feedback. 3 decades of failed boules that taught engineers what the next boule needed. Coherent, which absorbed the silicon-carbide substrate business of II-VI and traces parts of its lineage further back still, carries a comparable depth of process history. Together with a small number of Japanese producers, these companies have supplied the bulk of the global silicon-carbide substrate market. The market is not diversified across dozens of competitors. It is concentrated in a small number of producers who spent the 1990s and 2000s learning a process that most of the world was not paying attention to. Think of the substrate market as a specialty flour milled by 2 or 3 producers who have spent 30 years perfecting the grain. You can open a bakery anywhere in the world. You can hire excellent bakers and buy first-rate ovens. But if the recipe requires that specific flour, you call those 3 producers, because no one else has cracked the milling process at the quality and volume you need. China's device fabs are excellent bakeries. The flour is still mostly imported. Why didn't China build its own substrate industry from the beginning? The honest answer is, they tried. The problem is that silicon-carbide substrate manufacturing requires a process learning curve that capital cannot compress on a short timeline. Every boule run teaches something about the next one. Starting the learning curve later means starting behind. And the physics of crystal growth does not accelerate simply because the investment is larger. So where exactly is China on that curve today? Chinese companies do produce silicon-carbide substrates domestically. SICC, based in Shandong, and TanKeBlue are the most prominent domestic producers, publicly documented companies with real production output. Some of their material has been qualified by domestic device fabs. The direction of travel is real, and dismissing it would be a mistake. But reported self-sufficiency of around 20 to 30%, again, industry estimates, not independently verified data, means the device fab floor still rests predominantly on imported material. The remaining 70 to 80% is not a rounding error. It is the structural dependency. The gap is not in whether China can grow silicon-carbide crystals. It is in whether it can grow them at the defect density and diameter required for high-volume, high-yield device fabrication. The current production standard in the industry is the 6-inch substrate diameter. Growing boules at that diameter while maintaining the defect levels that device fabs require for acceptable yield is where the process learning gap is most acute. Independently verified defect density or yield figures comparing Chinese domestic substrates to Wolfspeed or Coherent equivalents are not publicly available, which itself tells you something about the state of the comparison. Getting the furnace to produce a crystal is like getting dough to rise. Getting it to rise without a single structural flaw large enough to ruin the loaf, batch after batch, at production scale, is the part that takes a decade of practice to learn. The first part is hard. The second part is categorically harder. Here is what makes the second part so unforgiving. In a silicon carbide boule, a threading screw dislocation is a single misaligned column of atoms. It begins at or near the seed crystal, and as the boule grows upward, that dislocation grows with it, propagating through the entire crystal, millimeter by millimeter, until it is present in every wafer sliced from that column of the boule. You cannot quarantine it to one section. It travels. A micropipe is worse. A micropipe is a hollow defect tube running through the crystal along the growth axis, essentially a channel of nothing where crystal should be. In a power device, a micropipe causes catastrophic breakdown under voltage. The device does not degrade gradually. It fails. And you do not find the micropipe by inspecting the wafer under ordinary light. You find it when you test the finished device, after you have already spent the full processing cost. The wafer looked fine. The device is gone. Reducing these defects, micropipes, threading screw dislocations, basal plane dislocations, across large diameter boules grown at production speed, is the central unsolved yield problem for newer entrants to this market. The industry as a whole has made dramatic progress over 2 decades of work. Micropipe densities that were once significant obstacles at the 4-inch diameter have been reduced to very low levels at leading producers. But that reduction happened through exactly the kind of iterative process feedback that takes years of high-volume production runs to accumulate. Each failed boule is not a waste. It is data. But the data only compounds if you are running enough volume to iterate fast. Think of it like a crack in a window. If it starts at the bottom edge, it does not stay there. It climbs. In a silicon carbide boule, a dislocation that begins at the seed crystal does not stay at the seed crystal. It climbs with the boule as it grows, woven into every wafer you cut from that section. Better furnace control reduces the probability of starting that crack. It does not guarantee you will never start one. And guaranteeing near zero at production volume across large diameters is the part that requires years of accumulated runs. This is the physics of why the substrate gap is harder to close than the device fabrication gap. Processing a substrate into a chip requires mastering a set of techniques that are genuinely difficult, but they are learnable given the substrate. Growing the substrate in the first place requires mastering a process whose failure modes are invisible until late in the cycle, whose defect propagation is physics rather than chemistry, and whose learning curve cannot be bought off the shelf. Now consider what this means strategically, and what the leverage looks like from the outside. The United States has moved to restrict some exports of silicon carbide-related materials. Export controls on silicon carbide substrates and related crystal growth inputs have been discussed, and some restrictions implemented under existing frameworks, though the precise current scope is not fully public. The lever exists. What it can and cannot do is more nuanced than a simple on-off switch. China's device fabs can stockpile substrates. That is a real buffer that buys time. But stockpiling does not close the process learning gap. It defers the pressure. The strategic question is whether domestic substrate producers can reach high-yield, large-diameter production at scale before an external supply squeeze becomes severe enough to bite. And that timeline is genuinely uncertain. The revenue generated at the chip layer creates the resources to push harder at the crystal layer. That logic is straightforward, even if the specific budget allocations are not public. China has built a commercially strong device fabrication business, and the returns from that business fund the substrate research and development effort one layer down. The chip layer is not just a product. It is the financial engine for the supply chain independence campaign below it. The foundation of this whole structure is still partially rented. The upper floor is real, well-built, and generating revenue. The foundation beneath it, the silicon carbide crystal, is mostly supplied from abroad by companies with decade-plus process learning advantages that cannot be replicated quickly. That is the actual shape of the dependency. Here is my honest read. The triumphalist version of this story says the substrate gap is a detail. China makes the chips. The chips are in the market. The rest will follow. The dismissive version says the dependency makes the entire power chip effort fragile, and that Wolfspeed and Coherent hold the decisive card. I think both are wrong, and the reason matters. The chip layer strength is real, durable, and generating the commercial momentum that funds the substrate push. That is not a minor achievement. But the process learning moat in crystal growth is also real, not as a permanent wall, but as a years-long delay whose specific timeline nobody can call with confidence. The most accurate read is that China has built something genuinely impressive on a partially rented foundation, and the race now running is between the domestic crystal growth R&D timeline and whatever pressure the external supply situation creates. Nobody knows which one arrives first. That uncertainty is the honest answer, and anyone who tells you otherwise is working from conviction rather than evidence. The floor China has raised in power chip fabrication is genuine and durable, but a floor resting on an imported foundation is not yet a floor you own. The crystal beneath the chip is where the next raise has to happen, and the physics of boule growth does not care how much capital is allocated to it. Here is what I want your honest read on. The chip layer China controls is strong enough to generate real revenue and fund the crystal growth push from below. But the substrate foundation is still mostly imported. Does the strength of the upper floor buy China enough time and resources to secure the foundation on its own terms? Or does the substrate dependency become a pressure point before the crystal growth gap actually closes? Tell me which layer you think decides this, and why. I want to know where you stand on it, in the comments. If you want to follow how the crystal growth race actually resolves, including when Chinese domestic substrates start appearing in volume and what that does to Wolfspeed's position, subscribe, because this story is not finished. One silicon carbide wafer, grown abroad, shipped to China, built into a chip, sold as domestic. That gap is the story, and it hasn't closed yet.